Hi everyone. In this video, I would like to go over some of the questions from chapter 17 of your textbook. So I'm just going to go ahead and get started. It says, which of the following solutions is a good buffer system? Well, in order to make a good buffer, we need a weak acid and a conjugate base. Or we need a weak base and a conjugate acid. Both will work, but we have to have one of these two things. So it says, which of the following solutions is a good buffer system? Well, here we have HBr and potassium acetate. In this case, we have acetate, which is the conjugate base of a weak acid, acetic acid, but HBr is a strong acid. So HBr being a strong acid, that's not going to work. 0.1 molar NaOH and 0.1 molar KOH. NaOH is a strong base and KOH is a strong base, so those are both strong bases. That's not going to work. A solution of 0.1 molar HI, a strong acid, and 0.1 molar ammonium ion. In this case, the ammonium ion can be thought of as a weak acid. It's actually the conjugate acid of ammonia, a weak base, but HI is a strong acid, so that's not going to work. A solution that's 0.1 molar acetic acid, a weak acid, and 0.1 molar lithium acetate, or acetate ion, which is a weak base. Sorry, it is a weak base, but it's also the conjugate base of acetic acid. This is the correct answer. If you're taking the General Chemistry 2 lab, you actually made a solution of acetic acid and sodium acetate, and both were around 0.1 molar when you did that lab experiment. Question 2 says, a 1.0 liter buffer solution is 0.05 molar acetic acid and 0.25 molar sodium acetate. Which of the following actions will destroy the buffer? Well, because this is a 1 liter buffer solution, it means we have 0.050 moles of acetic acid because it's 0.05 molar in 1 liter. And we have 0.250 moles of acetate. So if we were to get rid of all of the acetic acid by adding a base, that would destroy the buffer. Or if we were to get rid of all of the sodium acetate by adding an acid and converting it into acetic acid, that would destroy the buffer. So let's see what we've got. Adding 0.05 moles of sodium acetate. That's not going to destroy the buffer. It'll raise the pH slightly, but it'll still be a buffer because it will still contain acetic acid. Adding 0.05 moles of KOH. If we add 0.05 moles of KOH, we won't have any more acetic acid. This acetic acid will all be converted into acetate, technically potassium acetate, but they're just ions floating around in solution. So the acetic acid will become acetate. If it becomes acetate, we have no more acetic acid, we no longer have a buffer. Let's just check the other answers. Adding 0.05 moles of HCl. Adding 0.05 moles of HCl will destroy some of the sodium acetate, but there's plenty more. So we still have 0.2 moles, if you will, left. So that won't destroy the buffer. And again, adding 0.05 moles of acetic acid, it'll still be a buffer because it'll still contain sodium acetate, and it'll just be a slightly lower pH because we have a little bit more acid. So the answer here, as we already talked about, is choice letter B. Number 3 says, if the pKa of formic acid is 3.74 and the pH of a formic acid sodium formate, or weak acid, conjugate base, solution is 3.89, which of the following is true? Well, there's several things that we can look at here, but I'm going to write out the Henderson-Hasselbalch equation. pH equals pKa plus log, in this case, concentration of CH2O minus over concentration of HCH. This should be CHO2. This should be CHO2. So It's pH equals the pKa plus the log of conjugate base over weak acid. Well, in this case, if we notice, this is the pKa, and it is lower. This is the pH, and it is higher. So from a common sense perspective, if the pH is higher than the pKa, there has to be additional base. From a mathematical perspective, we need the log of this to be positive. In order for this to be positive, the number on the top has to be larger than the number on the bottom. Said another way, this ratio has to be greater than 1. So, in both the common sense perspective of the pH is higher, so there has to be more base, or from the mathematical perspective, there has to be more base. In either case, we need to have more base. So it says the acid is far greater than the base. That can't be right. The acid and the base are equal. That can't be right. If the acid and the base were equal, the pH and the pKa would be the same. This would be 1, and the log of 1 is 0. The acid concentration is greater than the concentration of the base. No. The acid concentration is less than the concentration of the base. So this is the correct answer. So this is the acid, this is the conjugate base. The conjugate base concentration has to be higher because the pH is higher than the pKa. Number 4 says, calculate the pH of a solution formed by mixing 100 milliliters of 0.2 molar HClO with 200 milliliters of 0.3 molar KClO. So weak acid and its conjugate base. And then it gives us the Ka for HClO, which is 2.9 times 10 to the minus 8. So the first thing we might want to consider is the Henderson-Hasselbalch equation. pH equals pKa plus log concentration of hypochlorite, which is ClO minus, over the concentration of HClO, which is hypochlorous acid. So we have ClO minus over HClO. There's a couple problems here. First of all, we are not given the pKa, we are given the Ka, so we can solve that problem first. The pKa equals the negative log of the Ka. Well, in this case, the Ka is given, so we take the negative log of that using our calculators, and we get 7.54. So now I know the pKa of this. Now I have to do log of ClO minus over HClO. Now it might seem that we could just plug in these numbers, but there's a problem. The problem is that we don't have the same volume of solution. When we mix these together, we have 300 mLs of solution, but we only added 100 of this and 200 of this. So we need to use the dilution equation. So to find the concentration of HClO, we need to use C1V1 equals C2V2, where the initial concentration is 0.20 molar. The initial volume that we used is 100 milliliters. The final concentration, that's our variable, that's what we don't know, that's C2. And the final volume is the total, or 300 milliliters. When we do that math, we find that C2 equals 0.067, that's a 0, molar. All right, we need to do the same thing for the KClO. So the concentration of KClO, again, we want to use C1V1 equals C2V2. The initial concentration of the KClO is 0.30 molar. The initial volume of the KClO is 200 milliliters. The final concentration, again, is the variable. And the final volume is, again, 300 milliliters. When you do that, we find the final concentration in the solution of the KClO is equal to 0.20 molar. Now we can plug in. We have pH equals the pKa, which is 7.54, plus log of 0.20 divided by, make that a little bigger, 0.20 divided by 0.067. And when we do all that math, we find the pH is equal to 8.01. And it makes sense that the pH is slightly higher than the pKa because we had slightly more conjugate base than we did of the weak acid. So this is how we could find the pH, and in this case it's choice letter B that is our answer. All right, number 5. This is a tough question. It says a 1.50 liter buffer solution is 0.25 molar HF and 0.25 molar sodium fluoride. All right, so HF and F minus. It says calculate the pH of the solution after the addition of 0.1 moles of solid sodium hydroxide. And then it says assume no volume change on the addition of base, and it gives us the Ka is 3.5 times 10 to the minus 4. So as in the previous question, we can use the Henderson-Hasselbalch equation to solve this, but not exactly directly. So the pH equals the pKa plus log of, in this case, F minus over HF. All right, so in order to solve this, we need the pKa. Well, the pKa is the negative log of the Ka, which in this case is equal to, if we take the negative log of this, 3.46. So that gives us the pKa. But now we need this F minus and HF. Well, we have a bit of an issue here. So we need to look at the fact that we're adding sodium hydroxide, and the sodium hydroxide we have to know is going to react with the HF. Why is it going to react with the HF? Well, the HF is an acid. Acids react with bases like sodium hydroxide. So in this case, the HF is going to react with the NaOH to form F minus. Which is probably better written as NaF, okay, and H2O liquid. So we can use what is similar to an ice table, okay, but when we do this, we have to use moles and not concentrations. So we have the initial, the change, and the final, and then we're going to have to convert that to concentrations. So there's kind of a lot going on here, and I'm glad you're watching the video because I'm not going to be able to probably accurately display this in writing. So what first thing we need to do is we need to figure out how many moles of HF there are in the initial solution. So if we have 1.5 liters of this and 1.5 on second thought, I'm going to do this a slightly different way. Instead of using these in moles, I'm going to use them as molarities. So in this case, we have 1.5 liters of 0.25 molar HF, which means we start with 0.250 molar HF. For the sodium hydroxide solution, since there's no change in volume, we can do it this way. We need to find the molarity. There's 0.1 moles in 1.5 liters. Molarity is moles per liter. 0.1 divided by 1.5 is going to be 0.0667 molar. So all of these are molar, molar, and molar. NaF is also going to be 0.250 molar because that's what's given in the problem. Now, in the case of the acid, we are going to remove the amount of NaOH. So we're going to start with 0.25 molar, and we're going to lose 0.0667 molar, which is going to be the change minus 0.00667. In the case of the NaOH, we're going to react all of it, so we're going to lose 0.0667 molar. And in the case of NaF, because the HF and the NaOH react to form more of this, we're actually going to add 0.0667 molar. So because the HF and the NaOH react, we are going to lose HF. We're going to lose all of the NaOH, so the final amount of NaOH is 0, and we are going to gain some NaF. So we lose HF, we lose all the NaOH, and we gain NaF. Now we need to find the final concentrations of these things. When we take the HF and we subtract 0.250 minus 0.0667, we get 0.183 molar. When we take the NaF and we add 0.250 plus 0.667, we get 0.31, and I'm going to round it to 7 molar. So this is basically what we get. Now we can finally solve this question, this Henderson-Hasselbalch equation over here. So the pH equals the pKa, which we found before, 3.46, plus the log of the F minus concentration, which after we added the NaOH is 0.317 molar, over the HF, which is 0.183 molar. When we do that, we get that the pH is equal to 3.69. It's not surprising because when these things had an equal concentration, okay, the pH and the pKa were the same. So the pH of the solution should have been 3.46. We added some base and that pH went up, but it didn't go up a lot because it's a buffer. So this is the pH of the resulting buffer solution. And this is a quite challenging question. Number 6 says, when titrating a weak monoprotic acid with NaOH at 25 degrees C, what will happen at the equivalence point essentially if we look through these answers? So let's think about this. We have HA aqueous reacting with NaOH. And at the equivalence point, all we're going to have in solution is NaA aqueous, essentially A minus, plus H2O liquid, because these two things will be equal at the equivalence point. So therefore, what's in solution is just these two things, which is NaA, and NaA is A minus. But remember that A minus is the conjugate base of HA. So in solution, we're going to have a base. Well, if we have a base in solution, the pH of the solution will be greater than 7, because greater than 7 means basic. So when you titrate a weak acid with a strong base, the equivalence point happens above 7. And exactly the opposite is true. If you take a weak base and you titrate it with a strong acid, the equivalence point will be lower than 7 because you'll have a weak acid in solution at the end of the titration. Number 7 says, a 100 ml sample of 0.18 molar HClO4 is titrated with 0.27 molar LiOH. Determine the pH of the solution after the addition of 30 milliliters of LiOH. This is a challenging question. So let's take a look. First of all, HClO4, perchloric acid, is a strong acid. So we have HClO4 aqueous reacting with NaOH aqueous to form NaClO4 aqueous plus H2O liquid. So this is basically what we have. So what we want to do is we want to realize that the HClO4 in this case, if there's extra of it, is going to give us the pH. And if there's extra NaOH, that's going to give us the pH. So whichever one there's more moles of here is going to give us the pH. So in this question, I want to work in moles instead of in molarities, but you could work in molarities if you converted it to 130 milliliters. I think it's a little easier to work in moles. So we have the initial, the change, and the final. So in the case of the HClO4, the strong acid, we have 0.1 liters, so this is 0.1000 liters of 0.18 moles per liter. So if we multiply this by 0.18 moles per 1 liter, we end up with 0.018 moles of the HClO4. So initially, we have 0.018 moles of this. What about the LiOH? Well, in this case, we added 30 milliliters of 0.027 molar, so we convert this to liters, 0.0300 liters, and we multiply it by this molarity, and we find that there are 0.0081 moles of the NaOH. So in this case, we can clearly see there is more HClO4 than there is NaOH. So we're going to lose all of our NaOH because there's less of it. And we're also going to lose some of our HClO4 to form NaClO4 and water. And we're going to lose the amount that we have of NaOH, which is 0.0081 moles. When you do the subtraction, you find that finally you're going to have 0.0099 moles of HClO4. And from the NaOH, you're going to have 0 OH, but because it's in water, you're going to have approximately 0 OH minus. However, in order to find the pH, pH equals negative log of the concentration of H3O plus, and the concentration of H3O plus is equal to the concentration of the strong acid, we need to realize that this isn't a concentration. This is the number of moles. In order to find the molarity, we have to take those moles, 0.0099 moles, and divide by the total volume in liters, which is 0.1 plus 0.03, which is 0.130 liters. And when you do that math, we find out that it's 0.076 molar strong acid. We can then plug in pH equals the negative log of 0.076. pH equals 1.12. Because the concentration of strong acid, so this is the molarity of the HClO4, the strong acid, is equal to the concentration of H3O plus, and the pH is still 1.12, even though we've neutralized, give or take, half of the acid originally present in solution. All right, so now we're switching gears away from the acid-base chemistry and towards the KSP chemistry for the next few questions. So in this case, it says give the expression for the product solubility or the solubility product constant, KSP, for PbCl2. So we have a reaction, PbCl2, solid, is somehow in equilibrium, favoring the solid, with Pb2 plus aqueous plus 2Cl minus aqueous, because this breaks up into a lead 2 plus and 2Cl minuses, right? This is negatively charged negative 1 charge. There's 2 of them, so this has to be plus 2, and that's basically what it dissolves. Well, KSP is just like any other equilibrium constant. It's products over reactants. So KSP equals products, concentration of Pb2 plus, concentration of Cl minus squared over reactants. But there's a problem. The reactant's a solid. Remember, we only put aqueous and gases, things that have concentrations, in our equilibrium expressions. So in this case, we do not put the PbCl2, which is why the KSP doesn't have a bottom term, because they all work this way. So what we get here is choice letter E. Question number 9 says, calculate the molar solubility of thallium chloride in 0.4 molar NaCl at 25 degrees C, and it gives us the KSP for thallium chloride. So essentially here what we have is we have a common ion effect. So sodium chloride has chloride in it, and thallium chloride has chloride in it, so it's going to decrease the solubility of thallium chloride. And then it asks us for the molar solubility. So let's go ahead and do that. So let's look at the reaction first. And I did this example before in question 8. But we have thallium chloride, solid, is somehow in equilibrium with thallium plus aqueous plus Cl minus aqueous. And we know that the KSP of this, again, it's products over reactants, but the reactant is a solid, so it just doesn't go in there, is the concentration of thallium plus concentration of Cl minus. So if we want the molar solubility, we're essentially looking for the concentration of thallium, okay, that it's going to be present in the solution. We know the KSP, but we have to consider the concentration of chloride. So we can use here an ice table. And we don't need to worry about the thallium chloride because it's not soluble, so it doesn't really have a concentration. So we're going to use these in molarity units. So the initial concentration of thallium is 0. But the initial concentration of chloride is not 0. It's 0.40 molar. How much is there going to be a change? Well, we're going to add X amount of thallium, and we're going to add X amount of chloride. So at equilibrium, we'll have X thallium, which will give us the molar solubility, and for chloride, we'll have 0.40 plus X. But here, what we're going to do, we're going to ignore X because it's small relative to 0.4 molar. So we're going to go ahead and ignore the X. Now we can plug in. KSP, which is given 1.7 times 10 to the minus 4, equals X times 0.40, not 0.0 plus X, because then we'd have to use the quadratic equation in order to solve it. We divide here. This shouldn't be minus 7. This should be minus 4. It's 1.7 times 10 to the minus 4. We need to divide by 0.40, divide by 0.40, and we get X equals 4.3 times 10 to the minus 4, which is the molar solubility of the thallium chloride. The answer here, it differs a little bit in sig figs, so we get 4.2 times 10 to the minus 4. On my calculator, I got 4.3, but I think they're close enough. So it's choice letter D. Number 10 says, in which of the following solutions would AgCl expected to be the least soluble at 25 degrees C? Again, this is a common ion effect. So if we look at this, NaCl breaks up into 1Na and 1 Cl minus. So the concentration of Cl minus, in this case, is 0.250 molar. MgCl2, on the other hand, breaks up into Mg2 plus and 2 Cl minus. So the concentration of Cl minus is actually double the concentration of MgCl2, or 0.50 molar, because MgCl2, solid, breaks up into, and this one is soluble, so it's not really reversible, Mg2 plus aqueous plus 2Cl minus aqueous. So whatever the concentration of this is, the concentration of Cl minus is double. In this case, if it's 0.25, it's 0.50. In this case, the concentration of Cl minus is the same as the concentration of KCl, or 0.250 molar. And in this case, same thing, because there's one lithium and one chloride, the concentration of Cl minus is exactly the same as the concentration of LiCl, which is 0.250 molar. So which of the following solutions would it be the least soluble? Well, that's the one with the most common ion, which in this case, the most Cl minus. Because remember, the common ion effect is that if we have AgCl solid in equilibrium with Ag plus aqueous and Cl minus aqueous, the more Cl minus that we have in solution, if you think about Le Chatelier's principle, the more we're going to form the solid, and therefore the less soluble the solid is going to be. So in this case, we have twice as much Cl minus, so we're going to have decreased solubility. So this is choice letter B. All right, so the last one. It says, determine the molar solubility of lead-2 sulfate in pure water. And it gives us the KSP of lead-2 sulfate. So we have PbSO4 solid dissolving to form Pb2 plus aqueous plus SO4 2 minus aqueous. So this is the reaction. And we know that the KSP for this reaction, KSP, is equal to the concentration of Pb2 plus times the concentration of SO4 2 minus. It's very important that we know the polyatomic ions in order to be able to solve this. So we are given the KSP. So we know this, but we don't know these. Well, how are we going to do this? Probably not surprisingly, we're going to use an ice table. So initially, when we first dissolve this solid, there's none of this and none of this. We're going to gain X amount of lead and X amount of sulfate, because its stoichiometry is 1 to 1. And at equilibrium, we'll have X lead and X sulfate. So if we do this, the KSP, 1.82 times 10 to the minus 8, equals X times X. So you plug in these equilibrium amounts. I'm just going to flip it around. X squared equals 1.82 times 10 to the minus 8. Now, I need to take the square root of this, the square root of this, and I get that X equals, technically plus or minus, but the positive answer is the only right answer, 1.35 times 10 to the minus 4 molar. And this is the molar solubility of lead-2 sulfate. So I used an equilibrium table. I solved, in this case, very similar to question 9, except in 9 there was a common ion effect, and here we're just dissolving the lead-2 sulfate in pure water. So that's the end of these questions. Since it's only one chapter, I only came up with 11 questions, but they do kind of broadly go over several of the different concepts that are presented in chapter 17. I hope you found this video useful, and I do appreciate you watching.